Hi everyone, in this video we are going to learn about non-homogeneous recurrence relation, and in our previous video we have gone through homogeneous recurrence relation and that link was provided in the description. Now coming to this non-homogeneous recurrence relation, it is further classified when it is consisting of distinct roots and when it is of equal roots. So firstly, if you can see this relation like C naught an plus C1 an minus 1 plus and so on ck into an minus k, which is equal to f of n. See, in the case of homogeneous recurrence relation, we are having 0 in the place of f of n, but in the case of this non-homogeneous recurrence relation, here we are having some function or else some constant value. Okay, so for such types of a relation, its general solution is given by an is equal to an power h plus an power p. Here this, see, if the equation is in this form, like for a non-homogeneous recurrence relation, its general solution is given by an is equal to an power h plus an power p, where an power h is nothing but our homogeneous recurrence relation and an power p, which is nothing but particular solution. We'll discuss about these two firstly. So let us consider this to be case 1. See, whenever you have f of n equal to some constant value, okay, if f of n is equal to some constant, like it is like a value of 1 2 3, like that, okay. In this case, so let us consider an example of this case 1 where your f of n as being a constant value. So for this, if you can see here, you are having an minus 2 an minus 1 plus an minus 2, which is equal to 1, which is nothing but some constant value. In the place of f of n, here you are having a constant value. Now our first step is to find homogeneous solution. So in order to find homogeneous solution, what should we make it? That is an minus 2 an minus 1 plus an minus 2 equal to 0, right? So in order to make this into homogeneous solution, first step is to put a power n into in the place of a power n, an, we have to replace with r power n. Please go and watch my previous video if you haven't watched it. So put an is equal to r power n. Now on substituting r power n in the place of an, we'll get r power n minus, in the place of n minus 1 you have to place n minus 1. So minus 2 into r power n minus 1 plus r power n minus 2. Since here your lowest degree is like n and the difference of n minus 2, which is nothing but 2. Now you have to divide this entire equation by r power n minus 2. On dividing the entire equation by r power n minus 2, now this is your final equation and you have to find the roots for this equation. Since we know that for one, you'll get the roots as, for this equation, r square minus r plus 1. So on taking r minus 1 into common, you will be having r is equal to 1 comma 1. Now since you have got equal roots, so previously we have discussed that for the same roots in the case of homogeneous recurrence relation, our general solution will be c1 plus c2n into r1 power n, right? So c1 into c2n into, here r1 is nothing but 1, so 1 whole power, like into 1 power n, okay, into 1 power n. And this is our equation, right? That is an equal to an power h plus an power p. Now we have found this first part, that is an power h, and now our second thing what we have to make is, we wanted to find this particular solution, that is an power p. So in order to find this particular solution, we have to substitute an is equal to p in the given equation. Now what is the given equation? So we are provided with this equation, that is an minus 2 an minus 1 plus an minus 2 equal to 1. So you have to replace an with p. Now it gives you p minus 2p plus p, no matter whether it is n minus 1 or n minus 2. You have to just simply replace this an like with the p, okay. First, this is our first step. So as you can replace an with p, you will be having p minus 2p plus 1, plus p, okay. So on doing in such way, which is equal to 1, right, you will get 0 equal to 1. That means our rule is failing here. Now our second step is to make an as np. Now you have to replace an with np. Now our equation, see, I'll explain it again. See, here you are provided with an minus 2 an minus 1 plus an minus 2 which is equal to 1. Our first step is to place an equal to p in the entire equation, no matter whether it is of an minus 1 or an minus 2, you replace with p only. This is our first step. Okay, so p minus 2p plus p, which is 2p minus 2p means 0. 0 equal to 1. Is it true? No. So our rule is failing. Now we have to replace an with np. Okay, an with np in this equation, and again by placing an equal to np, minus 2 times of an means that is n minus 1 into p, and again a n minus 2p, which is nothing but n minus 2 into p. Okay, now on simplifying this, you will get again 0 equal to 1. That means here also your rule is going to be failed. Now you have to take again a n is equal to n square of p. Okay, now it is nothing but on substituting this again, that is n square minus 2 times of n minus 1 whole square p plus n minus 2 whole square times of p. Okay, on substituting in that way, you will get this value, that is you will get p as 1 by 2. Now your general an will become, that is your an power p, which is nothing but n square p, right? So what is the value of p? We know that value of p is equal to 1 by 2. So now your an power p is nothing but n square into 1 power 2. So I'll explain this particular solution once again. If you haven't understood, listen this. See, firstly you have to take an equal to p, and if doesn't satisfies, then take an is equal to np, then n square p, then n cube p. Like that for every value you have to check. See, an is equal to p. If this condition fails, an is equal to np. If this condition also fails, you have to take an is equal to n square p. If this condition also fails, an is equal to n cube p, and so on till you get satisfied. Maximum for n power 4 or last one till n cube or n power 4, it will get satisfied mostly. Beyond that you will not get. See, first as we are taking an is equal to p, just place that constant p in term of this, like in this term. Okay, that is p minus 2p plus p. You will get 0 equal to 1, and then you are taking an equal to np here. Since n is also involving, wherever you have n minus 1, you have to place n minus 1, and wherever you have n minus 2, you have to use that n minus 2 also. Since your an equal to np, and this is your question, so an, which is nothing but np, minus 2 times of an minus 1, which is n minus 1 into p, an minus 2, which is n minus 2 into p. In that way you have to check. If your rule fails, you have to go to the next value, and if your rule is not failing, then you automatically get the value of p at that instant. And we know that here we have considered an is equal to n square p, right? So this an power p is n square p. Since we find the value of p here, your an power p, that is your particular solution, will be n square into p, that is n square into 1 by 2. Now our final solution is an is equal to an power h plus an power p, right? This is our an power h which we have found, that is your homogeneous general solution for your homogeneous recurrence relation, and this is at a particular solution, that is an power p. The sum of this general solution of homogeneous and this particular solution is nothing but your non-homogeneous recurrent solution, that is an equal to an power h plus an power p. Now since your an is equal to an power h plus an power p, we got the value of an power h in this way and an power p in this way. So your an power h, which is c1 plus c2 into 1 power 1 plus an power p, which is this. So this is your general solution now in the case of a non-homogeneous recurrence relation. But if any condition is mentioned, see, if any condition like the value of a0 or a1 is not mentioned, then stop till here. But if in question a0, a1 and so on, such value is mentioned, then you have to proceed further. That is, as in the case of homogeneous relation, how we have made it, here also we'll do in the same way. That that is, here if any condition is mentioned, for suppose, let us suppose they have mentioned a naught equal to 2 and a1 equal to 5, then on comparing this we get the n value as 0. So substitute the n value of 0 in the entire equation, then you will get the value of c1, and then substitute n is equal to 1 since they have given you the value of a1. So on substituting a1 is equal to, in the place of n you have to place 1, then you will be getting c2 value. Since you have got c1 and c2 value, now our general, that is final solution will be 2 plus 5 by 2 n into 1 power n plus 1 by 2 whole 1 by 2 n square. This is your final answer in the case of a non-homogeneous recurrence relation. Okay. And you know this thing that this is for same roots, and whenever you get like distinct roots in the case of a non-homogeneous recurrence relation, you have we have already learnt in last video that for a homogeneous recurrence relation, when it is having of like distinct roots, your general solution will be in this way, right? That is c1 into r1 power n plus c2 into r2 power n. You have to make your an power h in this format when the roots are different. Okay. If you want to understand this non-homogeneous recurrence relation clearly, please go and watch my homogeneous recurrence relation. Then only you will be able to understand this topic in a very clear way. So this is our first case when f of n is constant. And now we are going through our second case. That is when your f of n is not constant and it is also a polynomial. See here, your f of n is so on comparing this both equations, here your f of n is a constant value, but in case if this f of n is also a polynomial instead of this constant value, then how can you solve that question? This is your case 2. Okay, when f of n is a polynomial of degree m, that is, so let us suppose your f of n to be c naught plus c1 c1n plus c2n square plus and so on. So if your equation is in this way, that is f of n is equal to c naught plus c1n plus c2n square plus and so on cm into n power n. So let us consider this example. You will be able to understand the difference between those two cases. So now this is your question, that is cn minus 8an minus 1, which is nothing but 5 plus 14n. This means it is also not equal to, this is not equal to constant, and this is also a polynomial of a certain degree. So here this is your question, that is cn minus 8an minus 1, which is equal to 5 plus 14n. What is our first main task? Our main task is, see, this general solution an is equal to an power h plus an power p. Our main task is to find an power h. So in order to find an power h, whatever may be at this right side, you have to equate it to be 0. Since in the case of this homogeneous solution, on the RHS side you don't have any value, you have only equal to 0, right? So you have to make this as equal to 0. Now this is not your cn, this is your an. So an minus 8an minus 1, which is equal to 0. Now on putting an equal to r power n, so we get r power n minus 8 r power n minus 1 equal to 0. So previously when you have r power n minus 2 and r power n, then your degree will be n minus n by 2, that is nothing but 2. So we are dividing with n by 2, n minus 2. But in this case you are having your degree as n minus 1, that is highest minus lowest, right? Highest degree minus lower degree you will consider. So n minus of n minus 1, this is of degree 1, so you have to divide with r power n minus 1. Now on dividing this equation with r power n minus 1, we get r minus 1, which is equal to 0, so r is equal to 8. So your homogeneous equation will be an power h, which is nothing but c1 into r1 power n, right? So since here you are having only r value as 8, so an power h is equal to c1 into 8 power n. Now we have finished finding this an power h, and now our task is to find an power p, that is particular solution. For this question we have two parts. See, for any type of question in this non-homogeneous, our first part is to find homogeneous solution, like homogeneous recurrence relation, and second one is to find the particular solution. Now our second step is to find an power p. In order to find an power p, let us consider an is equal to d naught plus d1n plus d2n square plus and so on dm into n power m. So for this particular solution, now your an is equal to d naught plus d1 power n. See how here you may get a doubt, how we are getting this an is equal to d, why we are considering only an equal to d naught plus d1 into n, means here we have got in this way, right? That is 5 plus 14n. So here you should consider only till two terms, that is d naught d naught is nothing but your constant term. See here you have you are provided with 5 plus 14n. 5 plus 14n in your question, right? So here d naught is nothing but a constant, and after that you will be having d1 into n. See, if you wanted to find an power p, you should consider an equal to in this way. But till you have only 5 plus 14n form, you should stop for here. Now your particular solution an equal to d naught plus d1 into n. Now you have to substitute that in the equation, that is in our question, that is an minus 8an minus 1, which is 5 plus 14n, right? So your an will be d naught plus d1n minus 8 into d naught plus d1 into, instead of n, here you are having n minus 1. So n minus 1, which is equal to 5 plus 14n. Now on solving this and equating this on both sides, take constant terms and take this term which is involving n as common, and this all constant terms to be common, and on comparison you will get the values of d1 and d2. Since you get the value of d1 and d2, you know your an power p now is d naught, that is d0 plus d1 into n. So since you know the value of d naught and d1, your an power p will become minus 3 plus minus 2n. Okay, and our final solution will be an is equal to an power h plus an power p. Since we got an power h to be c1 into 8 power n, so an is equal to an power h, that is c1 into 8 power n, and an power p, which is minus 3 minus 2n. Okay, and this is all about case 2 in the case of a non-homogeneous reconciliation. And again you will be having case 3, but this will not this is not much important, but we wanted to study it for sure. See, whenever you have fn as exponential function, see, previously in the first case we are having fn to be constant, like a particular single integer value, and in the second case you are having like a polynomial, like a linear 1 degree polynomial, and in this case you are having something raised to the powers in exponential form. Okay, when fn is an exponential function, that is when fn equal to p into a power n, then its particular solution is given by an is equal to d into a power n. Okay, see, this is our question. For example, an minus 8 times of an minus 1, which is equal to 5 into 2 power n. Already we have found the homogeneous solution for this. Here just only, instead of this 5 plus 14n, here we have consider as 5 into 2 power n. Okay, so for this homogeneous solution, we get homogeneous solution, like homogeneous recurrence relation, as an equal to c1 into 8 power n. And for in order to find this particular solution, we wanted to consider that we have given with f of n as 5 into 2 power n, and we know that an equal to d into a power n, right? So an is equal to d into a power n. Now you have to substitute that value in this given question. See, this is our question, right? That is an minus 8an minus 1, which is equal to 5 into 2 power n. So you have to replace it with, since we know that an is equal to d into a power n, right? For this particular solution, in the case of an exponential, an is equal to d into a power n. So an, which is nothing but d into 2 power n, n minus 1. So d 8 times of d into 2 power n minus 1, which is equal to 5 into 2 power n. So on simplifying this, see here you are having d into 2 power n minus 8 times of d into 2 power n minus 1, which is 5 into 2 power n. So we can write this as 2 power n minus 8 into d power. You can write this 2 power n minus 1 as 2 power n by 2, right? And here you are having again 5 into 2 power n. So this get cancelled. That is d into 2 power n minus 4d into 2 power n, which is nothing but 5 into 2 power n. Now on taking this 2 power n as common, you will be left over with d minus 4, which is 5 into 2 power n. Okay, now on comparing on both sides, you will get, on comparing both sides, you will get minus 3d into 2 power n, which is equal to 5 into 2 power n, which means minus 3d equal to 5, and you get the value of d as minus 5 by 3. This is just simplification, and your an power p is nothing but d into a power n, right? So it is nothing but minus 5 by 3 into 2 power n. And what is your final answer? An is equal to an power h plus an power p, that is an power h is nothing but c1 into 8 power n minus an power p is nothing but minus 5 by 3 into 2 power n. And if anything like a0 and a1 is mentioned, we will solve it further on replacing that n is equal to 0, n equal to 1. In that way you will find the value of this c1, and finally you will get an solution. So this is all about non-homogeneous recurrence relation. So let us have a quick recap what we have made till now. In this non-homogeneous recurrence relation, we will be having here it is equal to some value not equal to 0. Okay, first case, if this f of n is equal to some value like 1, 2, 3, like an integer, then you will solve in like in case 1 how we have made the, in that way you will solve. But if here you will be having 3 cases. First case is when f of n equal to some constant value, and your second case is when f of n is a polynomial of a certain degree m, and case 3 when it is an exponential function. Okay, so based on the type of question, you have to identify whether we have to apply case 1 or case 2 or case 3, and then you have to solve the question accordingly. If you have any doubts regarding this topic, please go and watch my homogeneous recurrence relation also. Mostly you will get your doubt to be clarified. And if you have more than that, like any suggestion or improvements to be made, please feel free to ask me in comment section. Thank you for watching, and this is all about our homogeneous recurrence relation and non-homogeneous recurrence relation. By this we have successfully finished our homogeneous and non-homogeneous recurrence relation. Thank you for watching, and subscribe my channel for more informative videos only if you like the content. Like, share and comment.